All right. I hope there would not be any more problems. Okay. And all right. Is everybody able to hear me? Praveen, Santosh, Subbareddy? Great. 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 I think now everybody is up and there are two more persons who are trying to connect and then we can start right away. All right. So if you have any questions, we can discuss that or we should right away start with our discussion. All right. Let me recap a bit on what we had discussed earlier. So in the previous session, we had talked about how does a recommendation system work. So there are many algorithms which generate the recommendations, and the simplest one is where we try to figure out. Yes, recording has been started, super ready. So so what do we mean by recommendations? We are trying to figure out, based on the historical preferences of the user, what would they like. All right. Okay. Damodaran, are you able to hear me clearly now? Is everything okay? Yes. So problem was not on your side. Problem was on my end actually. There was internet connectivity problem on my end. So the webinar was trying to get ended. All right. Again and again. Great, great. So the way our recommendation system works is we analyze the historical preferences of the user and then we try to predict what will they like. Okay. So a common way to do it is using first preparing who is closer to who looks like who, and then do sort of a cross sell that Sandeep liked this movie, you may also Kumar may also like the same movie because they are too similar. So that's what I'm trying to explain here. So Sandeep and Kumar are one third similar, meaning they have a similarity index, as in the common between Sandeep and Kumar is one movie, and the total number of distinct movies are three: Matrix, Casablanca, and Shawshank Redemption. So their similarity index is 1 by 3. And similarly, if there is no other user similar to Sandeep, then no other users so close to Sandeep, then we will first take the preference of Kumar, who is so similar, and then start giving Sandeep the recommendation of Kumar's movies and Kumar the recommendations of Sandeep's movies. All right, and that's what we are doing. So we are telling Kumar because Sandeep Sandeep has also liked Casablanca. You may also like it. Similarly, we are telling Sandeep that Kumar will also like. We are telling we are giving similar recommendations to Kumar. All right. Now, how to exactly do it? You don't have to write an algorithm for it. And reason is when you start doing this, it becomes really a big data problem. Why is this a big data problem? The third V, if you remember the third V, variety. When we talked about variety, it meant that it's not only the variety of the data, it's also the variety of the problems that you are trying to solve. Okay. So, and here that variety plays a big role, because if you imagine comparing all the users with each other, and then out of that you try to figure out of so many users which one is most similar to Sandeep as well as Kumar, and then same thing you do for Kumar and everybody. You try to, if you think about it, it's a complex algorithm. It will take a lot of CPU as well as it will take a lot of memory. All right. Therefore, if this algorithm could be broken down into a distributed technology such like Hadoop, in which this all clustering of the users, comparing of the users is happening parallelly on multiple nodes, and that would result in really great processing. And that's what Mahat did. Okay, that's what Mahat did. Mahat converted all these algorithms to big data, and and that's how the recommendation generated. For us, everything is just prepared, and what we can do is start using it right away. Okay, I'll show you. So first and foremost, let me try to explain why we are doing all of this. So Mahat is expecting from us a comma separated file in which there would be three things. Okay, this particular algorithm which we are going to use, this particular algorithm which we are going to use is going to have three columns in it. One is user ID, item or product ID, whatever you want to call it, and the rating. So based on these three columns, it will start giving you the prediction. All you have to prepare is prepare this three column data. And that's where most of the development effort, whether developers or data scientists, their effort go in. Okay, this effort of translating your input data into product ID, user ID, and the how much this user likes this particular product, that effort, a lot of effort goes into reaching to this level. For example, when I was working with InMobi and I had to build the recommendation, the actual recommendations was far more easier. The problem was a lot difficult because I was trying to do using the Apache server logs. That's a completely unstructured data. So based on, let's say you are playing a game and your game is requesting an ad from InMobi. So we have a log of this one. Similarly, you might be requesting again and again many different kinds of ads from InMobi. So based on this, we were able to figure out that you have been playing this game so many times as well as you have been playing it continuously. That means that means you really like this game. Based on this, we inferred the rating of the user, that this person likes to play this game and this much, just based on that logs data. And this is very important, and that's where Pig, Hive, and all of these MapReduce tools come into play to clean up the data for the consumption of these data science tools. Running a data science tool is far more easier, but cleaning up the data, preparing the data for a tool like Mahat is very important. So we'll just take an exercise here. All right. So let's say we have got this data, 1 million ratings of the users from Movie Lens. You will never get this kind of a clean data in real life, honestly. Okay. So let me try to log in. Is everyone with me? So keep asking questions or keep responding quickly so that I know that I'm not disconnected from the internet. Great, great. All right. So I'm logged in here, and this is my account. So here I have already prepared, already downloaded this rating. Let me delete ratings.csv. Okay. So this is my ratings.dat, and you can have a look at it. So here, see that? So this is the data we have. Luckily, we have user ID, product ID, and the rating. Okay, and the timestamp. But the problem is that it is separated by double colon. And our task is to replace this double colon with a single comma. Okay, and remove the last column. We don't want this column. Hadoop says that, sorry, Mahat says that give me three columns. First one should be a login ID in a long, and second one is the item ID. Third one is the rating out of 5. So the data is almost prepared, just that we have to remove the last item and keep only these three items. All right. So we'll try it using multiple ways. So one, if the data is smaller, okay, if the data is smaller, you can quickly do something like a unique cell script. What we have done here is we have used awk script to split the data by double column and then print $1, $2, and $3. All right. But in real life, you never get such a small data that you can just do it on the local machine. So what we are going to do is we are going to run pig script. All right. So we can see ls sgiri, and there we have here ratings.dat. I've already uploaded this data. Okay. So I can say tail. No worries, because here on pig, tail doesn't seem to be a command. All right. So we are going to use pig to clean up the data. Okay. Here we are saying load ratings.dat using pig storage and split it by comma, double column, single column. Okay. That's what we are going to say. See. All right. So after that, we are saying store the data into ratings.csv. Okay. Let's see if it works or not. It says that I think the file already exists. That's the error. Yeah, the input does not exist. No worries. So we'll go cd asgiri, and then we do the same thing because we have given the relative path. Therefore, we have to go into the same folder. All right. So load ratings. Then after you have splitted the data by column, we are iterating over it and picking up 0th, 2nd, and 4th column. All right, like this. And then we let me also remove ratings.rating.csv, ratings.csv. All right, and then we say store cd into ratings.csv. So using pig, you can quickly clean up the data like this. The way we have just prepared our ratings. Is everybody on the same page? All right. So right now pig is executing and it's loading the data. It will split it by column. Now since our data has double column, therefore second value $1 is going to be empty, and that's why we are going to $2. We are skipping $3 because our input data is double column separated. Okay. So it says that it is successful. Can say all right, and we can say ratings.csv. Can see, so it has converted our input data into a cleaner format. Now that's what our Mahat wanted, so we can straight away, it's already copied to our server, so we don't have to copy it anymore. And then we can remove the previous temporary folders created by recommendations generated by Mahat, and In case your Java home is not set, you can set that. All right. Now is the actual command. So let me take it out. Let me take it out. So here we are saying Mahat recommend item based, and this is the particular strategy which is going to use. And then this is my input file, and this is going to be my output folder. All right, that's it. This is the code which will generate the recommendation for us. All right. Any questions on this? It'll take some time to execute because it takes around 10 to 15 minutes. And once it's done, you will see the result in the format as described here. Okay. So the result we will see is in this format. So this user may like this movie this much, and this movie this much, and so on. So this is the recommendation format which we'll get and which will be in the HDFS in the output folder. All right. So the other algorithms similar to log likelihood, they are Tanimoto coefficient and similarity cosine, and then Pearson correlation, and so on. So Damodaran's question is, Mahat results are normally delayed. That's correct. That's correct. Because Mahat internally, if you look at it, although we called a command called Mahat, okay, it's internally actually calling, it's internally calling the Hadoop. Okay, it's executing MapReduce job via Hadoop. So as we all know that all the jobs at Hadoop are batch wise and have a inherent delay, and therefore it's going to be very time consuming. But if you look at the brighter side, this same data, 1 million entries, it's actually impossible to get it done in R. If you have a little bigger data, say 10 million, it will be impossible to get it done through R, because it will overflow the RAM, it'll generally overflow your RAM, as well as the CPU will become the bottleneck. Sounds good to you? All right. So these use cases we have already discussed. Collaborative filtering, that these are Mahat's use cases. Collaborative filtering is recommendations. Clustering means clustering the users into various groups or say news items. Then classification, and then frequent item set mining. So these are the four classes of problem Mahat solves, and most of the algorithms are bucketed into these four groups. Okay. That's correct, Praveen. Praveen's question is, let me copy it. His question is, for Mahat similar likelihood to work, data format has to be in this. That's correct. Okay. So you can take a look at other algorithms and understand what kind of format they have. And also, based on your requirement, have a cursory look at these algorithms, when to use which one. Okay. But most of this log likelihood, Tanimoto coefficient, cosine, they are all for exactly same purpose. Okay. So their result varies only a little bit. The outcome varies only a little bit. So you will not get too much of an advantage of switching between these algorithms. All right. Okay, so today we are going to start our discussion on Apache Spark. All right. Is that all right with everyone, or do you have any more questions? So on one hand, our MapReduce job is going on. I'm just hoping that it finishes by the time we start our Spark discussion. So do you have any questions before we go on to Spark? Damodran is the only one who is responding. Srisha, Girish, Arvind, Kal, Kirupa, Praveen, Santosh, Subbareddy, Sujit, Urs. So, do you have any questions? So Subbareddy is saying that I think we left some topic in ninth for discussion. We'll take it later, no worries. Okay, it's a small component called Uzi. Okay, that will take it up. Nothing to worry. Great. So everybody is okay with moving ahead now. No questions. Awesome. And all right. All right. So our MapReduce was great and is actually quite useful if you have to do these analytics job in an organization. So Hadoop is great in the terms of if you are okay with batch wise processing, meaning if you are okay with a delay of maybe 10 seconds, 5 seconds in the execution of something, then Hadoop does a very good job. But sometimes, and most of the time, you are not okay with a delay. You are not okay with the kind of MapReduce, the latency posed by MapReduce. Okay. In those circumstances, Apache Spark is going to be really, really great for you. Another problem it solves is, first, other than being really, really fast, other problem it solves is that if you have back-to-back chained MapReduce, so the way our MapReduce processes worked was the data was in HDFS, our MapReduce cycle took it, okay? MapReduce took it and saved the data in HDFS, right? Now let's say there is another MapReduce phase. It will again pick the data from HDFS and then save it to HDFS. Now we all know that whenever we read the data from disk, it is inherently slow, right? The speed of a disk is around 100 times slower than the RAM. Okay, so if the same thing is replaced with, instead of HDFS, we replace it with RAM. Okay, so it becomes really, really fast. The other benefit of replacing HDFS with RAM is that we do not have to deserialize the data anymore because it's already loaded into RAM. Serializing requires a lot of effort. Similarly, coding against coding for serializing is a really, really painful. Okay, because most of our programming structures, everything has been tuned such that our objects, our whenever we say created an object, it's actually loading data into the memory, right? So this is exactly the difference which Apache Spark brings into play. It makes it possible to persist the data in the RAM so that multiple phases can use the same thing. And that's what is the very big benefit of having tools like Spark. The other quality which Spark provides you is the command line. Instead of creating the full program and submitting to Hadoop and then waiting for the result to come, here it provides you the command line where where you are basically sending the commands and getting the results instantaneously, getting the feedback. So I will show you this. Okay. Now, yes, I will talk about it, Srisha, in a minute. All right. It's a very good point. So I was telling you about this command prompt. It says no space left on the disk. Probably somebody is misusing the cluster. All right, looks like. So in these circumstances, you go to hosts and look at the disk space. So Hadoop 2 is full. Strange. Hadoop 2 is full. Okay. I don't know whose directory is this, but I'm going to delete it. Nothing. All right. So, yeah. All right. Let me just clear it up. All right. I think that should do. All right. So I'm hoping that. Yeah, there's some space available now. All right. It has resumed the work. Great. And so where log and all that. It's actually these all servers continuously require a lot of monitoring. All right. Okay. No worries. Yeah. I think it should work. This should be sufficient enough. All right. So yeah, I think that should be good enough, and we will clean it up again. Let me just restart one of the data node which is dead. All right. So while our while our Mahout is running, let me let me explain to this particular part. Although I have written down in the blog, if you guys are following the blog, and I've written down good questions on Spark, you should definitely have a look at it here. These are advanced questions, the part 2 one. Part 1 one is something which is very much recommended to all. Okay, so you can go to the part 1. Okay, so there also I've tried to answer your question. All right, now let me explain what exactly I mean. What are the negative points about Spark? The one of the biggest problem with Spark is that it consumes your lot of memory. It consumes a lot of memory on the cluster. It doesn't leave a breathing space to others. Okay, that means two Spark tasks cannot be executed so comfortably on a single node. Okay, because it heavily utilizes your available RAM on a machine. Therefore 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 Spark is going to have these challenges when there are multiple users executing their job on a cluster. Okay, so that's one thing which a downside about Spark. Okay, that's the only downside of Spark. Okay, coming back to the question here. All right, so that was about basics about Spark, that it utilizes your memory to deliver the results faster, and and therefore it's really fast as compared to MapReduce and disk. As per their claims, it's 100 times faster if done completely into the memory, and 10 times faster if done on the disk. It builds on the similar paradigm like Hadoop, and is well integrated with Hadoop. Is really well integrated, and as we are talking right now, it's actually improving. I'm on their developer list, and the kind of contribution, the kind of community is going on right now. It's just marvelous. For example, other than GraphX ML Lab, right now there is one more tool called Spark R, which is really good. Which is really good. Okay, and let me just show you the updated diagram. Okay, Yeah, here. This one. Okay. So in case of MapReduce, the user was doing this, and then if there are multiple phases, this is the problem being solved by MapReduce of of the Spark. Okay. And also have a look at this latency number. I will share these slides with you. All right. So Spark is the basics of Spark is on top of Hadoop Yarn, and it can work on EC2. It can work standalone, and it can also be run on Apache Mesos. So Spark is like MapReduce, if you remember our diagram, where it's actually competing with MapReduce. It can run on top of Yarn, meaning since Yarn is already installed on your cluster, you don't need to install a Spark everywhere because Yarn is anyway installed already. So, so via Yarn, Spark will get its work done by executing itself on every node. Okay. Similar thing it does using other resource managers. And in case you have a single node, single computer, and you are doing it just for testing purposes, then standalone is good. All right. Now the Spark can read from variety of the file system. So Spark is just a compute engine. Spark is just a compute engine which can utilize multiple kinds of resource managers which can read from every kind of database. Also, it does not have its own storage. It is just a computing engine. All right. In case you are utilizing HDFS on and it's running on Yarn, if your Spark is running on top of Yarn and under the same Yarn, same Hadoop, you have HDFS, then it can take care of the data locality as well. It will try to execute the computation near the data. We'll show you how to do the computation Spark. All right. These are the various components with which Spark interacts with HDFS, HBase, Hive, Tachyon, Cassandra, and even the Teradata. All right. So there are many systems which it can read from and write to. Even the MongoDB it can read from. Okay. Now on top of Spark Core is like plain vanilla coding platform. I'll show you how to do that coding. And on top of it, people build just like in case of Hadoop, people build Hive and people build Pig. Here also the same thing has happened. There's something called Spark SQL, which is completely compatible with Hive. Anything you have written in Hive can execute in Spark SQL. Then there is a streaming library. Somebody built a beautiful streaming library as in to handle the stream processing. Okay. And in place of Mahout, Spark guys came up with something called MLlib. And afterwards they came up with a beautiful library called GraphX. The way there was something called Giraffe, here it's GraphX. GraphX is a nice engine which can be utilized to do a lot of graph kind of work, just like computing PageRank, computing other graph properties. Okay, and and on top of Spark, you also got something called R. It's called Spark R. And good part about Spark R is that using Spark R, you can actually run any of the R packages on top of a Spark, and that's going to be a killer combination because in R there are humongous packages. There are humongous packages which there is no such library on machine learning that has so many packages so far. And Spark, I mean, the only problem with R was that it was running on a single node, and that's why we were not able to use it for a little big data which doesn't fit into the memory. That's why Spark R, which can utilize the memory of multiple nodes and run any of the R packages, is going to solve a lot of data science problems. Okay, and that is why Spark R is going to become really successful. Okay, so it has become part of the core of Spark right now. Okay, so these are main components of Spark, and these are quite useful ones. All right, now let's discuss about the core. Now we have already installed Spark on Hadoop 1.nobigdata.com. If you want, you can also download, and if you have a running cluster, you can also download it and unzip it and then run it. Okay. All right. So I've already installed it. It's not that big a deal to install it on Yarn. You just download a binary, which is okay. So our recommendations are done. Those who are interested, they can have a look at HDFS, and yeah. So you can see Hadoop fs minus ls as giri and recos. All right. So in this part R00, okay. All right. Now you can have a look at it. So it has generated a lot of recommendations for us. You can see that. Now you take this data, put to your web server, and start showing the results to your end users in the form of, after joining this data with users, and you make it in a displayable format, and this should be good enough to display to your end users. All right. So that was quick look at the result of Mahat. Now coming back to Spark, we will be using PySpark in this discussion. Reason being is easier, I mean, based on our understanding, it's easier for a new programmer to learn Python as compared to any other language. That's why we have kept this demo in Python. All right. So this is the end starting point at Spark. So this is a console way of getting things done. Then there is a submit command, to which after you have written the whole script, you can use Spark submit and submit your code and get it executed. All right. So this is the place. This is the command prompt of Spark where you can execute things and get it done. All right. Okay. So do you want to take a break for 10 minutes and then join back? All right. Question from Damodaran is that why is it using Python 2.6? Why 2.7 and 3 are available? Why? Because I have installed only Python 2.6. Okay, that's the reason. All right, let's take a break for 10 minutes. Back by 10:10. Right, so I'm back. Is everyone back? Should we start now? We have some question from Damodran. The question is it compatible with any Python? I think the minimum compatibility with respect to Spark is around 2.5. Okay, Python 2.5 onwards. So it's compatible with most of the Pythons, because most of the Pythons which is in production right now is either 2.6, 2.7, or 3.x. Great. So almost everybody is back. So I think we should start now. All right. So the basic concept behind behind the basic concept in Spark is the resilience dataset. Resilient distributed dataset, which we call RDD. Okay. So it's basically a collection of elements partitioned across the cluster. Okay. So the way we had input splits, we created input splits on top of HDFS blocks. In the similar way, kind of an analogous to input splits, we have something called resilience dataset. And this resilient dataset stays in the memory, and it is basically a representation of your data in the memory from HDFS. Now, this RDD can be persisted in the memory so that you don't have to load it again and again from anywhere. Okay, so run mm, if you are going to run multiple phases of MapReduce, so probably you can keep the RDD in the memory so that you don't have to load it again. And and that is why that's exactly the reason why it is great for real time processing, or online transaction processing makes a good use case for this kind of computation, because you can keep the data in the memory and you can get the processing done really fast. All right, now the RDD itself, although the HDFS itself is having an ability to recover from the failures, in the similar manner, RDD itself, the resilience distributed dataset, has the ability to recover from the failure in case, let's say, there are four nodes in our RDD. Node 1 containing some portion of data, and so on. Let's say the node 1 goes down. So the work which was on node 1 will get shifted to other nodes, node 2 as well as node 3. This way, even though it looks like it's in the memory, but still you get the functionality of the failovers. All right. In this RDD is essentially, if you think about it, it's a big array of elements. It's a big array of elements. Portion of these elements are on various nodes. Node 1 containing some data, node 2 containing some array of some elements of this array, and that way. Okay, so RDD, you can always, whenever you think about RDD, think about it like an array. It's a big array of which some elements are on one node, some elements are another node, and so on. Okay, so now let's try to create a simple. Uh, First, the simplest one is loading the data from our big.txt. Okay, So you have lines. So lines is an RDD. What we have done here is we have said lines equals to sc dot text file, and this text file is in HDFS. So it's loading the data from HDFS into the lines. So lines here is your RDD. So whenever you say lines, it will quickly tell you that this particular file is mapped as an RDD and it's a text file. Okay, so we have successfully loaded an HDFS file into an RDD called lines. We have created a fresh RDD. Now let's try to, so an array here is represented like this. Okay, this is my array. If I want to assign it to a variable, I can say whatever name of the variable and I can say this. So my array is a variable of type array. This is in Python. It's in local memory. Now if I have to push it to RDD, it's very, very simple. So I can say my array RDD equals to sc dot parallelize, okay, my array. And this particular element is an RDD representing an array which was in the memory. We have pushed it to the RDD. Okay, so essentially what we are trying to do is we are trying to move the data from memory or the disk, or local memory or the local disk or from HDFS onto an RDD. All right, is my voice clear? So Damodaran is saying, is RDD linked to Scala? Scala is a programming language in which most of the Spark has been written. Okay, and the Python is basically a wrapper around Scala. So whatever call you make using Python, it's internally calling the Scala code, the code that is compiled in Scala. Okay, so that's why it keep on showing you it's a Scala thing everywhere, right? Yes. So basically what these guys have done is they have created a very thin library in Python which is internally calling Scala code. Okay. So right now we have just created an RDD which is in the memory. One is representing lines is representing our file, and my array RDD is representing this data. Good, good. All right, great. Now moving on. All right. Now what can you do on top of RDD? Okay, you if you start doing things like keep on reading data from end to end, do the processing, put it back, then it is going to be extremely slow. Instead, what you want to do is you want to execute code near the data, near the RDD node. Everywhere, on everywhere you want to execute the code. So that coding strategy comes from MapReduce or similar strategy. So the kind of code, there are two pieces of code which you can run on RDD. One is called transformation. You write your transformation code and you send it to the server, send it to RDD and get it executed everywhere. So transformation is like translation. Okay, like for each, the way you have for each in pig, or the way you have map function in your usual MapReduce. Similar way, here there are many kind of transformations. The most simple transformation, let's say we have got this RDD. Okay, I'll take a very simple case. Okay, if you say take, or say, let's say collect. So collect will bring the data back to the local node. All right, you can see that it brought the data back to the local node, brought a copy of it. Now, in case you want to churn the data there, then and there, let's say you want to convert it into cube, you want to do a cube. So before that, you'll have to create a function called, let's say, CB. CB means, I'm just giving it a name called CB function, or we can say def CB, and whatever value you're passing here, okay, and we can say return x into x into x. Okay, so we have created a function called called CB, which takes an argument as x and returns cube of x by multiplying it 3 times. So we can test our function. This is a function which we have just created in Python. Okay, we can create such kind of function in Scala, Java, and all. Okay, now you can see that it's successfully working. This function which we have created in Python locally is working perfectly fine. Okay, you can also try with say 100. All right, now let's send this code to RDD and get it executed distributively. All you want to do is let the my dd my my array RDD, this particular resilience distributed data set. All you want to do is we want to cube each element of this array. Okay, we want to cube each element of this array. So what we can do is we can send this code to everywhere on each node by my array rdd dot map, and that's it. So we are sending, but by calling this map, what we are exactly doing is we are sending the CB function definition to each node and get it executed on everywhere. Okay, let me just assign it to, let's say, new RDD. Okay, new RDD dot collect. So it has quickly computed our cube and given us locally. Sounds good to you? This is probably the most simple program I could write. Everyone, any questions still here? Okay. So my array RDD is an RDD loaded. It could be loaded from anywhere. Right now, this is loaded from my local RAM. I moved my local RAM's data into an RDD by saying sc.parallelize. And after that, we are executing map function on RDD and passing our function as an argument. It's like passing the function pointer. So what exactly are we doing? We are taking the function definition which we have created locally, handing over to this map function and telling it, here is my code, take it and execute it on each element of this RDD. And parallelly on all nodes which contain this data of RDD, all those nodes will be executing your function on each element of this RDD. So Praveen's question is that RDD is like a repository, okay, or like a logic that sends data to all the nodes. So you can think of it like a repository, okay? It's like a data set. All right. Now Damodaran's question is, that means Python and dev tools should be installed on all nodes. Okay. So, all right, that's a difficult question to answer. And yes, so yes, Python will have to be, if you are using external libraries, you will have to basically install Python and DevTools on all the nodes. That's correct. Good, very good question. Right? Good. All right. Here, what we are trying to do is we are trying to compute the line length of each line out of this RDD. Okay. So whatever lines we had done earlier, so this is in Python, I would create later. So everybody is okay with transformations? All right. There are many other kind of transformations which are available. Damodaran's question is the RDD network infra look similar to what you have explained in in map? So it's a basically a logical, I mean, it's a logical thing, as in it's a logical construct from the program. Okay, RDD is like a logical construct from the program. There is no hardware infrastructure involved in creating RDD. Okay, all right. Moving ahead, the next part about Spark is there are multiple kinds of filter transformations. We talked only about map, where we passed a function which got executed on each and every element of the RDD. RDD is like a big array loaded on multiple computers. Okay. Now, you can also run things like filter. Map, in case of a map, what it does is it takes an element, produces an element and put it there. Which means if you have n number of elements in an array, the result is going to have n number of elements, same number of elements. But let's say you want to remove some elements out of this array called RDD. So we want to remove some elements and we want to do a qualification round. We want to say that all the elements which are qualifying this particular function should be should be removed. Okay, and these are the values which should be kept. Let's take a case in our one. So here you can see that 8 is even. Let's say we want to remove new RDD. Out of new RDD we want to remove all the elements which are even. Okay, or we want to just keep only the odd ones. So we want to say my filter, define my filter. Okay, and if so, what we'll do is we'll say x percentage 2, which means we are dividing this number by 2, and we are saying, okay, okay, so which means what exactly are we testing? We are testing if the number is odd, if it's divisible after dividing, if the remainder is 1, then it should return true, otherwise it will return false. So you can test it quickly. So you can see my f is returning true for 1 and 0 for false, and for 8 it's returning false. Can see that? So we have written a function which can quickly test whether an element is divisible by 2 or not. Okay, it will return only odd. So let's say we create a new RDD called only odd. Okay, and then we say, what was that data? New RDD. Okay, we will say only odd equals new RDD dot filter. And what is the criteria we are saying? MyF. So MyF is the criteria based on which the elements will be selected. And this MyF says that keep only the data which is odd. Okay. Okay. So you can see that 8 has been removed. So you have map, you have filter, and then you have flat map. In case of map, one value generated another value. In case of flat map, one value can generate many values. Okay, this flat map is very similar to our map reduces map, right? Where for each input, our mapper was able to generate many values. But here, the map is here, it's supposed to generate only one value per value in RDD. Similarly, here flat map will generate many values for a single value. Alright, so Damodaran is saying, can you explain this transformation with a simple example? Say 10 million of Verizon customer billing to sort the data quota. Okay, so let's say there are 10 million customers. Okay, 10 million customers, out of which you just want to say, let's say what you want to do is you have loaded this 10 million customers, okay, into an big array. Each each element of this array represents your customer object, and so on. Okay, now what we want to do is we want to first capitalize, or let's say round round off the bill amount. Okay, let's say you want to just round off the bill amount out of all the customers. In those cases, you will do a transformation. You will do a transformation called map, which will do the round off. Okay, now let's say what you want to do is, you next assignment you got is remove all customers which have no credit history. So what will you do is write a logic and execute it using filter. Make sense to you? All right. So basically, when you have huge data and you want to delegate the work to multiple nodes, you load this data as an RDD, and then you break your logic into transformations and actions. Under the transformation, you figure out whenever you have to. So transformation is done whenever you don't want to bring the data back to the node. Instead, you change the data and keep it on the individual node. So here we are doing the transformation, keeping the data back on the node. All right, but we are not bringing it back. Just for the demo purpose, we are bringing it back. All right. Similarly, we have another thing called group by key, which you can have a look. And moreover, you can have a look at all the functions provided by Spark. Now next one comes as action. So what exactly is an action? Action is the cause of any activity in Spark. If you remember in Pig, unless you typed dump, unless you said dump dataset, nothing happened, right? Nothing moved. Or unless you said store. So store and dump caused the whole process to start, right? In the similar, exactly similar fashion, you have actions in Spark. There were transformation which did the transformation distributedly on every RDD node, and then there are actions. And what do these actions do? These actions bring the data, consolidate the data, and bring it back to the node. You can take the analogy of an action as if it's a reduce phase. It's collecting the data and bringing it, uh, reaching to a result. All right. So let's say here, in our case, the one which we are running just now, what we want to do is we want to do the summation. And also this collect itself is an action. Okay. Now let's say we want to sum up all these values. We want to sum up all these values. So all we do is we define a function called mySum. All right. Let's say x and y, and then we return x plus y, mySum 1 comma 3. All right. Now here you can say reduce, and in the reduce you can pass your function name. You can see it's 28. All right. So this is our reduce function or our reduce action, which made it happen that it summed up all the values using our function. So you can see this. Okay. So yes, each RDD will have unique names. That's correct. Just like in your program, whenever you're defining a variable, you always use a unique name in the same fashion. But that does not mean that if there is somebody else, if you are also running a program in the network and you are also using the RDD with the same name, it's completely okay. It's completely okay. The internal name, the internal pointer to RDD has got a very different name. Okay. So you don't have to worry about the naming. If let's say I'm also running Spark, you are also running Spark right now on the same cluster, and and you are also trying to keep the name of the RDD exactly same. It's completely okay. We will not interfere with each other. Good question. All right. So this reduce function takes only two arguments and return one. Unlike our MapReduce code, where reduce function was taking many values as an argument and was returning single value, here reduce function only take two values. Okay. Now you might be wondering that in an RDD there are going to be a million values, and this reduce function is only taking two values and trying to generate the summary. How does it work? How does it work? It leads to how does it leads to the single value, even though this function is just taking two arguments? Let's say there are a million values and we are trying to compute the summation of those values. You want to just sum up all these values by doing an algebraic sum straight away. Now, so all we will do is we'll say myRDD dot reduce and then give the sum function. This sum function will be applied on all the values in pairs, and whatever is the result, again the sum function will be applied on the result in pairs, and recursively again and again until it reaches to a single value. Okay, that also brings us to a point. Okay, we'll also talk about this part. So just like combiner, your function has to qualify to become a reducer. Not every function can be a reducer. Okay, any function which, even if applied again and again, if gives the correct result, is absolutely okay. All right. If if we have a function like average, like mean or average, it's not a right reduce function. Why? Because if you try to compute the average of the average values, it won't work. It'll give wrong results. So actions bring the data back to the node, and reduce function is one of the actions, and count is another, collect is another. If you just want to take n elements out of the whole RDD, then you can use take n. All right. So here there is a rundown of an example. So let's say here. Okay. So let's say on a single node, let's say there is this lines. You can see. So this is our array of lines. We can also load it if you want. We can demo it also. And all we want to do is compute the sum of line lengths. Compute the sum of line lengths. So what we will do is we will first do the run a function on, iterate over it, and compute the line lengths and then sum it. It's as simple as that. But in case of uh, Spark, we will basically load the same thing in an RDD. Let me just try to load it in front of you. So let's say we say lines RDD equals to sc.parallelize, and we say lines. So lines SR is our RDD. Okay. Now all we want to do is compute the line length. Okay. Compute the line length. So we define a function called len, let's say as line length. Okay. Line length, whatever variable you are passing it here, we are returning length of x. Now we can test our newly created function by passing it. Okay, you can see that it has given us 3 as a result. Now let's try to do a map. So we'll say LLR, some name I'm just trying to give, line length RDD equals to line SR dot map, line SR dot map, and what was the function name? LL, right? So LLR, if you try to say take 10 elements out of it, or try to take 3 elements, it'll give us the line lengths. It gave us the line lengths of these ones. All right. Or if you say collect, so it gave us all the results. All right. Now, if you want to compute the summation of all of this, and imagine that this this is loaded on multiple nodes. So some portion is loaded here, some portion is loaded here, and some portion is loaded here. Parallelly, line length is being computed on 3 nodes. So these elements here on one node, this is on one node, second node, this is on third node. Now, when we run our summation, the sum on these line lengths. So what will happen is summation will be computed on this node first. So these two values will be picked up. Summation will be computed, which is 20. And then again, these will be added, which is 24. All right. Here there is no need to call it again. All we are trying to do is sum up the values in RDD. And the way it happens is we call the same function again and again till we reach a single value. Now after this, so each node we have reached to a single number. Like here we have reached to 24, 14, and again 24. And then on the driver node, as in here this console, all these three values will be brought and again summed up, and this will be the result. So all I'm trying to say is, then when we say reduce, or when we say reduce action, it is basically executing your function to summarize, to bring it down to a small value. So this is my text here. It's a text editor, Damodran. All I'm trying to show you is an example. All right. So your question is, can you explain the TextMate fully before trying? It's basically a text editor. In case of Windows, you can try Notepad, Notepad++, or Edit++. I'm using Notepad+. I'm using TextMate. Okay. So all I'm trying to say is, on a what we are trying to do is we are trying to compute the line length. Okay. Internally, when you have this kind of data and you are loading it into RDD, some portion is on one node, some portion is on another node, some portion is on third node. If you say compute the line length is being computed parallelly on all the three nodes by the way of executing map function, the way we had demonstrated just now. And afterwards, when you try to do summation, the summation of line lengths is being computed in stepwise fashion. First, these two are being summed, and after that, these two are being summed, and we have this value. Okay. Similarly, on node number 3, these two values are getting summed. All right. After, on the driver node from where we launched, the data is getting gathered. Okay. And again, the same summation function is being called again and again to reach to a single value. So is this clear to you now, Damodran? So we have computed the line lengths here. You can see these line lengths. Same thing. Now, if we have my, what was that function? I think sum function, right? Sum. Okay, let me just try to. All right. Now, if we run the sum function on the network, let me just define a sum function. I think I have already defined somewhere. Yeah, my sum is the one. So my sum computes the sum of any two values. If you try to give more values, it will just say it takes only two arguments. All right. So LLR dot reduce. Yeah, you see that? It has done the computation. I think there's a mistake here in the logic because there's somewhere we have missed something. Right? No worries. So yeah, we are able to successfully do these kind of computation using Spark. All right. In case you want to share some data with the whole cluster in a read-only fashion, you can use broadcast variable. The way we had distributed cache, in the same fashion, we can have the broadcast variables in Spark. If you let's say there is an Spark application which wants all of these nodes want certain data, that you can push it using a broadcast variable. All right. Next is the accumulator. Okay. It's quite often then when you run a program on all different nodes, you want the data or the reports from all the nodes to be reported back to you. Or what you want is you want to compute the progress, you want to compute the counters, or you want to generate the logs. In all of those cases, accumulators are very handy. Not in case of logs, but doing a counter or progress computation, you can use accumulators. Accumulators are one way kind of data. I mean, all these all the nodes are going to give the data continuously, and accumulators will keep on summing it up and will keep on reporting it. Okay, so by the way of accumulators, all the nodes which are doing the processing, they can report the status back to the user continuously, all of the nodes. All right, let's take a case of this word count example. Probably this is going to be more useful to you. Let me so when we load our big.txt, if you remember our big.txt, it was a big text file. Okay, the same one which we use for word count. All right, when we use this function called sc.textfile, what does it do? It basically takes up, okay, let me just increase the font a little bit. So yeah, so what does it do? It loads the data from HDFS into an RDD. Then we have lines to word function. We have just written a function called lines to words, and what it does is it splits the data by space. If you remove this, then also it works fine. I'll show you this. So lines is anyway we have already, oh, this is overwritten by something. Okay. So this is our lines. I've reloaded it. Next is this function. Now you can see lines to words, and let's test it. Sandeep space Giri space something. So it has converted that into an array. You can see that? It has converted, it's splitted the data by space. Alright, so that's our function. Now let's use this function to convert our data into words. So if you have a look at lines, let's say lines dot take 10 elements. So we are just taking the first 10 elements, and you see that the data in this array is basically a line. It's an array of lines. Okay, so we'll convert it into array of words by the use of line to words. If this function line to words is executed on each line, we should get the result. So we use flat map. Why? Because lines to word is returning more values than one. It's not returning only one value. So it makes sense to use a flat map in these cases. Okay. Now let's have a look at it. Words dot take 5. Now you can see that it has broken it down. When you see U in front of a string, it means it's the string is in a Unicode, in a UTF-8. Okay, you see that? So we have pulled the data on, we have converted our lines into one word per element. Okay. Now let's convert it into key value pair. Key value pair is every element can be normal object or any complex object, or it can be a key value pair, like a tuple. So 2kv is anything you give. Let's say I give it Sandeep. It will return me, it will return to me What exactly is wrong with this? Oh, so now you can see that it is returning to me the word comma 1. Remember the key value pairs? Now we have converted using 2kv, we can convert words into this. Now you can see words kv dot take 5. We are just doing like cat 5. You can see that all the words are converted into key value pairs. Now let's sum up. Let's create a function called sum, which basically does summation of values. Okay. Now we are using something called reduce by key. Reduce function we can call as reduce by key as well. So what it does is it groups the data by the key, whatever we have defined earlier using as key value, and reduce by key will reduce it as in group it and then call your function called sm on all the values to give you the summary. So you can see w dot take. Okay, so you can see that it's doing all of the magic now. So it has computed this the word count. Okay, now you want to save this data somewhere. Let's save it here. Okay, and I call it 11 July. It says that it has saved the data at this location. Let's have a look at it. So we'll say asgiri slash word count and get out of this. We say Hadoop fs minus cat and this. It's a directory. Let's have a look at it. What is there in the directory? Okay, let's just pick the parts. Now let me just do a cat. You can see that it has computed, it has saved the data into HDFS after doing the computation. And you must have observed the rate at which it did the job is just marvelous, right? Did you feel that it was faster than MapReduce? All right. So which steps are not clear in this file? I think this is the way I should be asking you. So Damodran is saying without those prints, it would have been more better. You mean these ones? Oh, you mean I got it. You mean these things it keeps on showing all the time. All right. Now Girish's question is, yes, Girish, go ahead. So Damodaran question is all these functions are pushed to each node. Yes, that's correct. All right. Now Girish's question is we are writing functions to solve big data problems. Yes, that's correct. So now, sometimes when your problem statements keep becoming complex and complex every day, then you may not like to use these kind of things. This is like using the raw programming to get the work done. Okay, you might be dealing with MLlib, Spark R, and all that. But to understand the basics is the most important thing. Yes. So Girish, if we could have actually done the same thing using Java as well, but it could have taken me more time to demonstrate you the whole effect of something being live, as in it's getting executed live, is lost the moment we have Java or maybe C++ where there is a compilation required. That is why I've chosen Python. Great, great. Any other questions at this point? So we loaded the file, we split it into words by calling flat map line to words, and afterwards we converted each word into key value. That can be done using map. While flat map is required when you want to convert one value into multiple, normal map is required when you want to convert one value into another value, transform each value. Okay? And then we do the reduce by key. Reduce by key means whatever is the first word in here, it'll be grouped by key. It's like saying group by, and what is the aggregation function of the group by? You pass it as an argument. Great, great. So I'm hoping that everybody understood it. All right. Sometimes you have to push data, and in those cases, a broadcast is a great idea. So you can see that we are using broadcast here. We are saying that broadcast these variables onto the network. Okay, and inside this, while we are doing map, we are removing all the keys which are part of the common words. Okay, so here the objective is to find the word count, avoiding the most common words. Okay, avoiding the most common words, and that's when these broadcast and accumulators come into play. Accumulator is great when you want to report the progress back to the user. So here, if you see, we are saying that return k0. Here there is a filter function which is saying, so okay, let me go back from the beginning. We loaded the data, we defined a broadcast variable, we defined an accumulator, and then for each value we split it into words. Okay, now out of the words we converted into lowercase, and then we also did converted each word into key value pair where value is 1. Next is okay, next is we remove all the words which are common. And how are we doing that? By having a filter function which says return true in case in case return k0 not in common value. Okay, so whatever k is passed to it, it will find check it in the common words, and that's it. Okay, and that's how it filters the data. After that, we will do a basic reduce by key to sum up the values, and that's all right. So this is how you can use accumulator and broadcast. Note the accumulator, we are just adding 1 to the accumulator. The other big use case when people realize that Spark is pretty fast and utilizing memory, Then some people came up with an idea of running the stream processing on top of Spark, and it has been fairly successful. Any questions here? All right. So before we dive into stream processing, let's understand what does it mean by stream processing or streaming, right? Let's take a case of the classic example which I worked upon, where at at at, at an e-commerce company, you have, on one end there are vendors who are updating the detail about products, the sellers who are updating the details about product, and on another end there are users who see the data. Okay, there are users who are buying the products. So as and when these vendors are updating the details, the page has to be recreated or image has to be updated, and all of these details have to be updated. And the data which is coming from these sellers, the changes that are coming from the sellers are really, really high in numbers. Okay, and it has to be pushed continuously. In those cases, you would like to use stream processing, and that's where I use stream processing. In a stream or in a queue, I was receiving all the all the changes done by all the all the users. Okay, all the sellers were doing changes and pushing it to a queue. And as part of stream processing, I was reading data from the queue and then doing the processing and pushing it to the databases. Okay, so the input to most of your stream processing is generally either Kafka. Kafka is a queue, or Flume. Flume is the way we had demonstrated earlier. We had demonstrated that you can run Flume and generate data. And then you had HDFS, where the data is being appended frequently. You had 0MQ and Twitter. So your objective in case of Spark streaming, the velocity part of our big data definition, where the data is coming at a really fast pace. In all those cases, you can use Spark streaming to process the input data. And and what okay, let's go a little more details. So Spark streaming or any streaming converts the input into batches. Okay, the main role of streaming process is to really churn the data fast and convert that into the batches, so that so that the batch processing will not take too much time. Okay, so so the inputs of the stream on one hand keeps on getting received by Spark streaming library, which converts that data into batches of input data and then pushes it to Spark engine. And after that we get the process data. Okay, so Spark streaming is receiving the live input streams, divides the data into batches, and Spark engine generates the final stream results to be stored. Okay, so here is another representation. The way it happens is these queues, whatever data they are pushing, it will be pushed into RDD, a big array where first element of the array is on time 1, and second element of the array is time 2, and so on. Okay, so on one end the data is coming in and is getting stored in the RDD. So so some of the records are on one machine, some of the records are another. Now when you are processing this stream which is coming from a live system, you would like to do it using multiple machines. Okay, the processing is running here, here, everywhere parallelly. Okay, and that's what Spark does. So all all a streaming library has to do is convert the incoming data into an RDD, and rest of the things can be very neatly done using Spark's API. All right. So Spark provides you reduce by key and the window kind of operation, where you can say that for this window execute this particular logic. All right. Let's say you have to compute the word count in the incoming data every second. So all you have to do is first create a connection to the data source and define a window size. Here I'm saying my window size is 1000 millisecond, which is 1 second. So all we are saying is connect to this local host at this point and start receiving data in the dstream format, and then you split line into words. Okay, rest of the logic is very familiar to us because that's what we did during our word count. Okay, so this will basically split the data into words, and then you can run the map function to convert it into key values, and afterwards you can sum it up, and then you can do the collect. So basically this logic, what we have just showed you, converted the input incoming data into batches, and then on the batches we computed the word count. So, that's exactly what stream processing does. Make sense to you? All right. Any questions up to this point? So Damodaran's question is the rule for processing are the functions we pass. That's correct. The rule, the logic, on what basis we should filter, on what basis we should convert, all of that is the function which we passed as arguments. So data set that is generated will be stored. Yes, of course. The way we here when we were doing the word count here, we said the store it in the HDFS. So we were able to store the data in the in the HDFS. In the HDFS, yeah. Yes. So Damodaran is saying that means the possibilities are endless. That's exactly the reason why you have MLlib as of today, GraphX, and there are so many beautiful libraries which are coming up, including SparkR. So these libraries are just coming up, and those are wonderful libraries available in Spark as of today. Okay. So yes, you are right. The possibilities are endless. So in case of Spark streaming, because Spark was not, the objective of Spark was not really doing the streaming. Okay. It just some people found out that the kind of latency being offered by Spark is good for their stream processing. Okay. That's where the whole Spark streaming or D-stream came into play. So here the whole game is about a class called dstream. Okay, so dstream does everything for you. Yes, Damodran, we have launched another Spark class. You can have a look at on our website. All right. So Praveen's question is Spark is best approach instead of Hadoop because of its advantages. So whenever you need the response time really fast, in those cases you can use Spark over MapReduce, not Hadoop, MapReduce, because as a matter of fact, Spark is part of Hadoop now. Okay, so Hadoop is really big ecosystem. So for lots of cases, there are two reasons, mainly 2 to 3 reasons. Okay, 2 3 reasons. Why would you use Spark? One would be quick response. Second would be libraries. In terms of libraries, actually now Spark is able to is having a far bigger library set as compared to MapReduce. Okay, but there is no solution to HDFS. There is no solution to HBase. There is no solution to Yarn offered by offered by Spark. There is no solution to any of this. It's only for computation. So Spark is great because it provides you a quick response. It provides you set of libraries, and it also provides you great set of libraries and quick response, and along with that it provides you the nice paradigm where you don't have to haggle with MapReduce. Okay, slightly better paradigm to MapReduce. Good, very good set of questions. Okay, now when your your main business, when your main business is Apache doing the stream processing, if you want to process the record, millions of record in a second, then Spark is not a great solution. You would like to go for very specific solution like Storm. Storm is great at doing the stream processing. It's It reliably processes unbounded stream of data. It can be used with any language. It has been tested on 1 million per second per node. Okay, and is really scalable and fault tolerant. So in case Spark doesn't fit your bill with respect to stream processing, you can have a look at Storm. It guarantees that your data will be processed, integrates with queuing as in all the Kafka and all of these queues, and and also works well with the database technologies. Okay, let's have few more comparison. So use cases of Apache Storm are real-time analytics, online machine learning, continuous computation, and distributed RPC, and then ETL. So those are the use cases of Apache Storm. Okay, let's have a quick comparison. So with respect to stream computing, Storm handles record at a time, while Spark handles mini batches. Latency is less than a second in case of Storm, and in case of Spark streaming, the latency is around few seconds. All right. So in case of a storm, the result is may have a record is processed can be processed multiple times. Okay, sorry. So in case of a storm, every record will be at least processed once. It might be processed multiple times, but in case of Spark, a record will only be processed once. So Storm takes this decision that in case it has to process the data really, really fast and in a reliable fashion, then it's okay to get a record being processed twice, okay, rather than skipping some data. All right. Now, implementation of Storm was done at Twitter when it was backtype. So Storm is fairly fast and quite stable as well, and has been there around for quite some time. The language of choice is any in case of Storm. Same is with Spark, now Python 2, Scala, Java, and Python. And okay, so the more important part is the production support. So Storm is supported by Hortonworks, while Spark is supported by Databricks. Okay. Now, in case of Storm, in case you need a technical help, there is no help available as of now. So that is probably one of the reasons people avoid using Storm. Right? Any questions at this point of time? All right. Now, before we go with NoSQL, I would like to go with Uzi first. That's one thing which we have missed. So question from somebody is, what are mesos? Mesos is just like yarn. What does yarn do? Let me explain to you. Whenever we give it a work, it tells us how many nodes are there, what is their memory status, and and whatever code we give it, it gets it executed on various nodes. Same is the case done by mesos. All right. So Mesos is basically a sort of an operating system which runs on a cluster. All right. Let's try to understand Uzi. All right. So I think we missed Uzi, and we will try to uh, define it, and then we can take it forward from I mean tomorrow. All right. And tomorrow we'll have some time for discussion also. Okay. So let's get back to MapReduce for Uzi. Okay. So what we saw in case when I demonstrated you the recommendations generated by Mahat, what all did we do? First, we downloaded the data first. Then we used Pig to clean up the data. Then after we have cleaned up the data, we had executed Mahat. If you look at it, this is like 4 5 steps, and this is like a standard step. If you have to do it every day, you cannot rely on person, and therefore you have to use a workflow manager, okay, such as Uzi. So you define your work in in a sort of a DAG, in a directed cyclic graph manner. A cyclic graph is something an interesting data structure in computing. So whenever I mean, DAG is everywhere probably. So whenever we have to get multiple things done in a sequence, you use UZI and you define your work in terms of directed acyclic graphs. Okay. So if you are getting confused with DAG, think of it like an ANT XML script. So who all have used ANT so far? ANT, or have you used Maven? Have you used Make? Have you used some other workflow tool? So what have you used? Okay, Damodran use Bitbake. Interesting. I have not used Bitbake. Praveen has used Ant Maven. Greece has used DSE. Interesting. Interesting. Good. So whenever you have to, get multiple things done. So instead of every time saying first do this, do this, do that, you create something called a dependency graph. So this project depends on this project, and that project depends on 10 more others, and so on. Okay. Yeah. So just like build tool, DAG executes in real time on the cluster. Okay. And Uzi is well integrated into the rest of Hadoop stack and is scalable, reliable, and extensible system. Other than providing an ability to execute these XML or workflows, it also provides you something called coordinator jobs. Okay, a job that is triggered by the server. If you are from Unix background, you must have used something called cron tab, right? Which basically executes your job periodically or on other criterias. Here, Uzi executes the work based on various criterias, based on time, schedule, or based on the availability of a certain data. Okay, so I'll show you quick examples on Uzi. So, but it's already 11:30. Should we carry on tomorrow? All right, let's carry on tomorrow because we'll have for tomorrow we have comparisons of NoSQL, then Uzi workflow, and then we have project. Okay, that's all for tomorrow. All right. Thank you very much for having the patience to deal with all the technical issues we had in the beginning, and see you tomorrow. All right. Thank you, Praveen. Thank you. Thank thank you, Damodaran. Thank you, Kirupa. All right. Have a great day ahead. Bye bye. All right. Thank you very much.